On January 14, 2026, the Hubble Space Telescope captured a fascinating new set of images, offering a detailed brightness map of the glowing halo that surrounds the interstellar comet 3I/Atlas after its perihelion. This image revealed an extraordinary phenomenon, a radiant glow extending over 130,000 kilometers into space, roughly one-third of the Earth-Moon distance. What makes this glow especially intriguing is its appearance, which goes far beyond the typical cometary display. While comets often exhibit tails shaped by solar radiation and the solar wind, the outflow from 3I/Atlas did not follow the conventional pattern of cometary tails, offering a unique perspective into the comet's behavior and composition. The brilliance of 3I/Atlas is not merely due to the coma, the cloud of gas and dust surrounding the nucleus, but extends to the comet's strange jet structure. When processed through the Larsen-Sechenina rotational gradient filter, which removes the symmetrical glow around the nucleus, a peculiar configuration of jets came into view. Among these, the most striking feature was the anti-tail. This anti-tail was directed precisely toward the Sun, which is in stark contrast to the typical cometary tail that is pushed away from the Sun by solar wind. This phenomenon suggests a very different physical interaction between the comet and its environment. Further investigation into the structure revealed not only the anti-tail, but also 3 mini-jets. These mini-jets were arranged in a highly unusual pattern, separated by an angle of 120 degrees from each other. These jets defied the expectations one might have for the behavior of a standard comet, where outflows generally point away from the Sun. This apparent anomaly prompted a re-evaluation of our understanding of cometary behavior, especially considering the unique trajectory and conditions surrounding 3I/Atlas. One of the more perplexing elements of 3I/Atlas's behavior comes from its periodic wobble. An analysis of previous Hubble images, including those from December 2025, revealed that the comet's jet structure shifts periodically by approximately 20 degrees over a span of 7.1 hours. This suggests that the jets are not fixed in one position, but rather undergo a dynamic process that alters their orientation over time. The orientation change between December 2025 and January 14, 2026 was relatively modest, around 5.6 degrees within a half-hour period. However, even this subtle shift could be crucial in understanding the forces at play around the comet and its outflows. The Earth will soon reach a unique alignment with 3I/Atlas, occurring on January 22, 2026, when it will be positioned within 0.69 degrees of the line connecting the comet and the Sun. This alignment is significant because it will provide us with an unparalleled opportunity to observe the comet at its brightest. The alignment will allow the comet's reflective surface area to be maximized as seen from Earth, providing a glimpse of 3I/Atlas as it faces directly toward the Sun. In this context, the anti-tail will be pointed directly at us, offering a rare visual event that promises to yield new insights into the comet's physical properties and behavior. The alignment also brings into question the true nature of the anti-tail. What is it about the anti-tail that enables it to survive in the harsh conditions of space, particularly the intense solar radiation and solar wind? In typical cometary tails, the material is often blown away from the Sun by these forces. However, the anti-tail of 3I/Atlas seems to defy this common understanding by maintaining its structure and orientation toward the Sun. This raises several possibilities about the composition of the material in the anti-tail. Could it be composed of large fragments of ice, as suggested in a paper I co-authored with Eric Keto? Or could it be composed of large dust grains, as I have suggested in a separate research note? Alternatively, could massive objects be involved, as proposed in a paper I published earlier? To explore these possibilities further, data from the SphereX Space Observatory has been instrumental. In the months leading up to Perihelion, SphereX measurements revealed the presence of icy fragments around 3I/Atlas, suggesting that water ice was a significant component of the comet's makeup. However, by December 2025, a noticeable change in the spectral signature of the comet was observed. The ice signature had disappeared, replaced by a variety of organic molecules, including CH3OH methanol, H2CO formaldehyde, CH4 methane, and C2H6 ethane. These compounds, which are rich in carbon, were detected in gas phase, indicating that the comet had undergone significant chemical changes after perihelion. The discovery of these organic molecules is significant not only because it highlights the changing nature of 3I/Atlas's composition, but also because of the implications it holds for the survival of these molecules. In order to withstand the extreme conditions encountered during its interstellar journey, the organic molecules must have been shielded beneath a thick layer of material, perhaps several meters deep. The presence of these molecules provides new evidence that comets like 3I/Atlas may harbor complex organic chemistry that could offer clues about the origins of life in the solar system. The enhanced water production rate of 3I/Atlas, measured to be around 20 times higher than expected, further supports the idea that significant changes have occurred in the comet's internal structure. This surge in water production suggests that the comet may have been losing material at an accelerated rate as it passed through perihelion, possibly shedding layers that were previously insulating the organic compounds beneath the surface. The combination of the anti-tail, the presence of organic molecules, and the extreme behavior of the jets all points to the comet being in a highly dynamic state, one that is dramatically different from the behavior typically seen in comets within our solar system. This dynamic state is also reflected in the interaction between the comet and the solar wind. The solar wind, a constant stream of charged particles emitted by the sun, usually causes the tails of comets to form in a predictable way, with particles being pushed away from the sun. However, the anti-tail of 3I/Atlas behaves in the opposite manner, extending toward the sun. This suggests that the forces acting on the comet are much more complex than the simple solar wind pressure. The anti-tail could be a result of a unique interaction between the comet's material and the solar wind, or it could be a consequence of the comet's own intrinsic properties. Further study of the anti-tail and the material ejected by 3I/Atlas will likely provide valuable information about the composition of comets and their behavior under extreme conditions. Understanding the mechanisms that allow the anti-tail to persist, despite the powerful forces of solar radiation and wind, could help scientists develop more accurate models of how comets behave as they travel through the solar system. It may also provide new insights into the processes that govern the evolution of comets and their role in the delivery of water and organic molecules to planetary systems. As more data from Hubble, SphereX, and other observatories become available, we may begin to piece together a more complete picture of 3I/Atlas and its anti-tail. The upcoming alignment of Earth, 3I/Atlas, and the Sun on January 22, 2026, will provide a crucial opportunity to study the comet in detail, especially the anti-tail's composition, structure, and behavior. It's an exciting time for scientists studying interstellar objects, as this rare alignment promises to deliver key insights into the properties of 3I/Atlas and its remarkable outflows. The continuing observations and analyses of 3I/Atlas and its anti-tail are part of a broader effort to understand the origins and evolution of comets and other interstellar objects. As we learn more about these distant travelers, we are also uncovering clues about the early solar system, the nature of organic chemistry in space, and the conditions that may have existed in the interstellar medium billions of years ago. The anti-tail of 3I/Atlas, with its strange configuration of jets and unusual interaction with the sun, represents a significant step forward in our understanding of the complex and dynamic nature of comets, offering new insights into the mysteries of the cosmos.